Hey there, this lesson is 8.2 and it's about using property of special triangles to solve problems. So we're going to use properties of special triangles. Special triangles like, um, well, 30, 60, 90 triangles is one type we're going to do it, and 45, 45, 90 triangles. We're going to talk about those. And these are actually special right triangles. So, here's a type of problem that we're going to try to answer after this. Let's go to, yeah. We're going to actually answer this question right here. We're going to answer it right away, but are there ways to find missing side lengths of right triangles? So right triangles, are there ways to find missing side lengths other than the Pythagorean theorem? Yes, there are, but only for two special cases. Really, the Pythagorean theorem and these two special cases are the only the main ways that you'll find them. So the two special cases we're going to look at today are 45, 45, 90 triangles. That just means that two of the angles are 45 degrees and one is a 90-degree angle. And then the second way is 30, 60, 90 triangles. So 30 degree, 60 degree, and a 90-degree angle. And these are very common triangles. They're very useful triangles, and we have special properties that we can use with them. So let's start off with the 45, 45, 90. And this is theorem 8.5. It says in a 45, 45, 90 triangle, both legs are congruent. Okay, since two of the angles are congruent, their opposite sides are congruent. It is an isosceles triangle. And the length of the hypotenuse is the square root of 2 times the length of a leg. So our hypotenuse would be equal to square root of 2 times a leg. You could rearrange that if you want and say that well, the square root of 2 is equal to hypotenuse divided by a leg. You could say that then if you divide both sides by the hypotenuse, you'd have 1 over a leg is equal to the square root of 2 times, or divided by the hypotenuse. There's different ways to rearrange it, but this is the form that we're going to keep it in. That's the easiest way to work with it. So an example that this might be useful in is, let's say you have right here, find x and y. If your answer is not an integer, you can just simplify the radical. So we know this is a 45, 45, 90 triangle because we have a 90-degree angle, and one of them is 45, so the other one has to be 45. X should be simple because it's an isosceles triangle. These two would be congruent, so x is also 20. Now, to find y, that's a hypotenuse, so it's got to be equal to the square root times a leg. So it's 20 square roots of 2, which that's reduced form, 20 square roots of 2. So that would be x, and that would be y. So it's just using that nice formula we got there for 45, 45, 90 triangles. And again, that only works for 45, 45, 90 triangles. So if you don't have a 45, 45, oh, there's the book. Got that book on most of these pages. If you don't have a 45, 45, 90 triangle, it's going to be tough to do. So, looking at number 2 is a little bit tricky because the hypotenuse is the square root of 24 times the square root of 2. But remember, the hypotenuse equals the square root of 2 times leg. So then, if the hypotenuse is 24 square roots of 2, that would be equal to the square root of 2 times a leg. And then to find the length of the leg, we divide both sides by the square root of 2. It also cancels out here, so that leaves us with the length of a leg would be 24. So x would be 24, since it's a 45, 45, 90. Y would also be 24. So that's how you work with one of those when you're given the hypotenuse, and it is with the square root of 2. Now number 3 is a little bit different because it's not given as in the form of a square root of 2. So we're going to have to work with it and do a little work. But we know this is a 45, 45, 90 triangle. These are congruent then. And to find x, well, let's use a different color here. I'm going to use blue. So if 16 is the hypotenuse, it's going to be equal to the square root of 2 times a leg. So we'll say x. Again, to solve for x, we divide by the square root of 2. So we have x equals 16 divided by the square root of 2. But there's a problem here. When we reviewed last time, we said you cannot have a square root on the bottom. So what do we have to do to simplify it so there's not a square root on the bottom? Well, we want to multiply it by itself on the bottom. Square root of 2, so that cancels out the square roots of 2. But in order to do that, we have to also multiply the top by the square root of 2. So you have 16 square roots of 2 over 2, which the 16 over 2 could then reduce. You'd end up with 8 square roots of 2 would be your answer. So that would be the value for x. Now here's a problem to think about. It says, it's a real world problem, an architect is planning a new town square. The square sides are 20 feet long. Choose our square, 20 feet long. A walkway will also cut diagonally through the square. Here's our nice walkway here. How long will the walkway be around to the nearest tenth of a foot? So again, we can use the Pythagorean theorem, or we could use this thing where we know the hypotenuse, so this is x, is going to be equal to, since this cuts in half, these are going to be both 45-degree angles. So x would be the square root of 2 times 20. So whatever 20 times the square root of 2 is. And we can round it to the nearest foot. I'm not going to do that right now, but actually figure out what it is rounded to the nearest foot. And that would be how you do it. So those are 45, 45, 90 triangles. Now the other special case, like I said before, is 30, 60, 90. So 30, 60, 90 triangles have a theorem as well, theorem 8-6. It says in 30, 60, 90 triangle, in a 30, 60, 90 triangle, the length of the hypotenuse is twice the length of the shorter leg. So that's an easy one. If you have the length of the shorter leg, whoops, they wrote in here. The hypotenuse is twice the length of the shorter leg. That'll always be the case for 30, 60, 90. The other one that's a little bit more hairy because you're dealing with a square root would be the longer leg is the square root of 3 times the shorter leg. So both formulas use the shorter leg in them. So that's the common thing there. So let's use this in an example. Actually, this is a proof. If you want to see the proof of why that works, pause it and take a look at this. This is actually the proof of why that theorem works. We're going to go down here and go to an example of how to use it. So number 1 says find x and y. If your answer is not an integer, express it in the simplest radical form. So we know that the hypotenuse is twice of the smaller leg. Smaller leg is always opposite the smaller angle. So the hypotenuse y would have to be twice the smaller leg, which is 15. So y equals 30. Seems to me like that's way easier than using the Pythagorean theorem. We only have one of the side lengths anyway. So this is also a great good thing to do. The longer leg, x, is the square root of 3 times the smaller leg. So x equals 15 square roots of 3, and that is reduced. So that's all we need to do for x and y. Number 2 gives us a little bit different. So number 2 gives us the hypotenuse. But the hypotenuse, 14, is equal to 2 times the smaller leg, which is y. So really, y is just 7. And then we can use that 7 with this to find x. So x would be the square root of 3 times 7. So that would be 3 square roots of 7. So really easy if you use those formulas. Let's look at numbers 3 and 4. See how these work. Number 3, there it is. Number 3 gives you the longer leg. So the longer leg formula would be, the longer leg would be 4 square roots of 3 equals the square root of 3 times the shorter leg, which is y. Alright, little algebra. To get y by itself, let's just divide by the square root of 3. Divide by the square root of 3. And y equals 4. Nice. And then remember, the hypotenuse is just twice of that, so that would be equal to 8. 4 and 8. Number 15, we're given the longer leg is 15. So 15 is equal to the square root of 3 times the shorter leg, which would be, let's say this is x. And this is like the last one we did with the 30, 60, 90, where we have to divide by a radical. Oops, I just divided by a double radical. I meant to do the square root of 3. So x equals 15 over the square root of 3, but that's not okay to have a radical on the bottom. So to get rid of it, we multiply by itself, and we do that to the top as well. And you'd end up with 15 square roots of 3 over square root of 3 times the square root of 3 is just 3, which when you reduce it would be 5 square roots of 3, because 15 over 3 reduces to 5 right there. Alrighty, one real-world example to look at for these would be number 2. The top of a giant slide is 30 feet off the ground. Giant slide. The slide raises at a 30-degree angle. Interesting. Here's our slide. 30 feet off the ground. This is a 30-degree angle. This is a right angle. That would be a 60-degree angle. To the nearest whole foot, what is the distance down the slide? So we're trying to figure out this x. And all we have is the longer side. So we got to figure out the shorter side first. So 30 equals the square root of 3 times y. Okay, this is y. So y would be equal to 30 over the square root of 3. When you multiply it by itself to reduce that, square root of 3 over the square root of 3, you'd end up with 30 square roots of 3 over 3, which reduces to 10 square roots of 3. So y is 10 square roots of 3. Okay, and I'm just doing these from memory, but then we know that to find the x value, that would be twice of that. That's 2 times 10 square roots of 3, which would be 20 square roots of 3. And 20 square roots of 3 to the nearest whole foot, I'll actually do that one. 20 times the square root of 3, square root of 3 times 20 would be 34.6, so 35 feet down. Alrighty. So that is how you use those two special case theorems. That was the 30, 60, 90 one. Alright, one last question for you to ponder. It says find the value of each variable. If your answer is not an integer, express it in a most radical form. We can do that using that thing, or using those theorems. A little bit more work because there's a few things to solve for. But here's one thought question. A classmate said that the perimeter of an isosceles right triangle can never be a whole number. So isosceles right triangle, it'd have to be a 45, 45, 90 triangle. Could it ever be a whole number? Is it true or is it not? And explain what your reasoning is. And then finish up by answering the closing questions, if you will. All right, that is all for section 8.2 on special triangles, 30, 60, 90, and 45, 45, 90 triangles and their properties or their theorems. All right, we'll see you.